Okay, so now the next talk will be a modular dielectric elastomer actuator to drive miniature autonomous underwater vehicles. We have a tag team presentation today by Florian Berlinger and Mihai Duduta.
Right. Hello, everyone. My name is Mishu. I'm excited to share our work together with my colleague, Florian, our work on a modular dielectric elastomer actuator that drives an underwater autonomous vehicle. You can see the robot there. I'll first talk about the soft fin that's driving the robot, and then Florian will tell you more about the robot itself. The reason we want to work on dielectric elastomer actuators is because we need more actuation technologies. We need more ways to create motion in soft machines that operate in the proximity of human bodies and human-centric environments. And if we're able to create movement in soft bodies with just electrically driven signals, then we can solve a variety of problems. You can see the 10 challenges that science robotics posed earlier this year. And we believe that you can tackle a large number of them, 6 we estimate, with better soft actuators. And dielectric elastomer actuators are one of the most promising technologies. They're soft elastomers, they're electrically driven, but if you've looked at the program for this conference, there's only about 4 talks that are on dielectric elastomers, and generally it's because the materials aren't quite there. Yes, these are soft materials, and they're driven electrically, and they should respond quickly. But generally, you need a rigid frame, as you see in this video. Which negates all the advantages of having a soft elastomer to begin with. You need a high voltage, which requires a large power supply. And the forces you get out of a single elastomer are pretty small. If you are trying to build a swimming robot out of DEAs, you probably will take one of the approaches that other groups have taken in the past, where using still the same frame configuration, you have your actuator move the frame and have some passive elements on either side of the frame. And if you do that, you can get motion. As you see in the example on the left, the robot works well, it's untethered. However, it has to use water, the surrounding water, as electrical ground. And another thing it does is you can't really separate the body of the actuator from the body of the robot. They're the same thing. The bulk of the robot is the actuator. If, however, you try to use multiple actuators, as Professor Floriano's group did a couple of years ago, and they showed it at IROS, you can have an actuator on either side of a flexible frame, and by applying voltage to one side or the other, you get this flapping tail motion like in their example fish. Building on their ideas, we wanted to use our own materials that we developed in-house. And our own materials are different because they do not require pre-stretch, so therefore don't require a frame to create motion. Our materials are acrylic elastomers. We combine them with carbon nanotube electrodes, which are extremely thin, and we can stack multiple of these actuators together to create a device that outputs larger forces than what was previously possible. By sticking together 2 of these unimorph configurations back to back using a flexible adhesive, we can make a bimorph. And when one side of the bimorph is powered, we get deformation that's fin-like, similar to the fin of a fish. And it works because one unpowered unimorph acts as a strain-limiting layer for the other unimorph. Once we had a method to make these, we wanted to evaluate them in a more quantitative fashion, and we wanted to make actuators that output large thrusts. And the parameters we had to play with were the number of layers, the actuation frequency, and the stiffness in each elastomer. We set the actuation voltage to the highest the materials could handle and the highest our power sources could output. Using this setup, we measured thrust in a variety of fins. We observed a signal that matched our expectation. We had peaks and valleys in thrust output. We averaged those, and then looking at flapping frequency, we found that some saturation above 3 hertz. Then we looked at the number of layers, and of course, as we stacked more and more layers, we got higher force output. Some fabrication limitation kept us at 17 layers per side, so 34 layers total in the fin. And lastly, we looked at the amount of crosslinker that we would put in the elastomer to tune its stiffness, and we found that middle-of-the-road elastomers that were as soft as natural muscles were actually the best performer. They moved the most and output the largest thrust. Out of that, we were able to create a robust multi-layer actuator that was sufficient to power a robot that Florian will tell you more about.
Thanks, Mishu. Now, having found the right trade-offs to build strong DEA fin-like actuators, our next question was, what can they do? And to answer this question, we built a miniature underwater robot, took one of our DEA fins, and ran several free-swimming experiments in a tank. Our robot is about the size of your palm. It's 3D printed for convenience, and it has complete autonomy. This means all the components to run the robot are inside the small and fish-like body. And those components include a battery, voltage boosters, a microcontroller, and also a pressure sensor that penetrates the hull. With this pressure sensor, the robot can autonomously measure and control its diving depth. To demonstrate several experiments with our robot, we made it reconfigurable. Trimming weights can be placed at either its anterior end to dive vertically, or they can be placed on its ventral side to swim horizontally. What allowed us to fit all of those components inside our small and compact body was our comparably low actuation voltage. Our robot requires 2,000 volts to actuate its DEA fins, and that's about 3.5 times less than comparable DEA-powered robots. In this voltage range, there exist small enough voltage boosters, the MCOs, on the right side here, and we took 2 of them and integrated them in our power circuitry. Speaking about power, the power consumption of our robot is just about 0.75 watts, and that allows for a runtime of more than 100 minutes. Now, we ran our robot in several experiments to demonstrate its maneuverability. Those experiments included planar swimming in horizontal direction at forward speeds of up to 55 millimeters per second, and also turning at turning radii as low as 1.2 body lengths. Turning was enabled by powering one side of the fin more often than the other side. Then we also demonstrated vertical diving at speeds of up to 30 millimeters per second. And finally, to add to the robot's autonomy, we used sensory feedback from a pressure sensor to demonstrate closed-loop vertical diving. And such a closed-loop dive between 2 set thresholds of depth is shown in this figure. The robot starts at the surface of our tank in the top left corner of this figure. It actuates its fin and gains depth until it crosses the lower of the 2 thresholds. When it crosses these thresholds, it switches the fin off and starts rising to the surface slowly. The robot rises because its body is slightly positively buoyant. It rises until it crosses the upper threshold, and there it switches the fin on again and repeats that behavior, resulting in the figure shown on this slide. Now, what you can observe as well in this figure is significant overshoot, and this overshoot is caused by the robot's inertia and could be mitigated in the future by applying more elaborate control strategies. What we could do as well, instead of diving between 2 set thresholds, we could also just set 1 threshold and hover at the given depth. Now, to sum up, what we designed is a more versatile dielectric elastomer actuator that is strong thanks to its multi-layer architecture. It's modular and soft since it doesn't require any pre-stretch, and it can be therefore easily mounted on any underwater robot. independent of the size or shape of this robot. So we basically decoupled the actuator from the robot. Our robot is completely autonomous, it's untethered, it's not connected to its environment in any way, and it shows an especially high degree of autonomy because it's using closed-loop control to automatically update its behavior. With this, I want to conclude the section about our current work, thank our co-authors and sponsors. In the future, we plan to explore several directions, including soft biomimetic actuators for soft robots. We can tune our fin to mimic more accurately the undulatory motion of fish fin, for example. And with such a robotic fish fin, we could then study fish swimming and reinforce hypotheses and findings from biology. Ultimately, going beyond the study of individual fish and robot, we are also designing an underwater robot collective to explore collective behaviors in 3D space. We are convinced that we need novel actuators, and our work with those DAs reinforced our belief that DAs are an attractive choice, especially for soft robots. And we just showed like 3 examples of where we plan to go, and we hope you will join us on this journey and also think about using DAs in your projects. Thanks for your attention, and we are happy to take some questions.
I see some questions there. Yeah.
Mishu and Florian, thank you for your great work and great presentation. So as far as I understand, you normally want to pre-stretch your dielectric elastomer actuator to achieve not only lower actuation voltages, but also to prevent mechanical instabilities and extend the range of deformation before you have electrical breakdown. And I'm wondering, how did you actually get around the need to pre-stretch, and do you actually suffer from any of those issues in your non-pre-stretched actuator?
That's a very good question. The reason for pre-stretch is to take the elastomer from one mechanical state to a different mechanical state where it's closer to strain stiffening behavior. We're able to program the same type of strain stiffening behavior by just adding a certain crosslinker. More details are in our paper, and I'm happy to discuss in more detail.
Thank you.
There's another one a few rows back.
Thanks for the wonderful talk. In the layers that you put in your actuator, were they all connected in parallel? And the second part of my question is, could you consider adding different degrees of freedom in the different layers with some method to get more degrees of freedom in your fin, maybe to produce waves and things like that?
Excellent questions. Yes, the layers are all connected in parallel. That makes it easy. You apply the same voltage across all of them. You get the same displacement, but you enhance the force. We are actively working on something like that. And since the work's not published yet, I won't share much more than that. But yes, there are very interesting ways to select which regions actuate versus which don't, depending on where you put stiffening elements or electrodes. So yes, it's a very, very interesting composite material to study.
Any other questions? We have time maybe for one quick one. Okay, thank you very much.